Greetings, in this one I'll focus on the interesting problem of 7 bridges of Konigsberg. So it's based on a historical scenario of a city that was the way it was back then, with 7 different bridges between different land areas. And the main question was, are we able, in the context I'll draw the city plan, are we able to cross all the bridges by the way that we cross each of them exactly once, but not more than once, and we may manage to cross all of them going in one walk. So take a walk across the city, crossing all 7 bridges such a way that we have to return to none of them for a second time before making it through all of them? And the answer is no. But it's not possible to very quickly find a systematical answer or like a systematical theorem straight away. The point of my endeavor here will be to conclude with a systematical theorem that answers why it is so. But first of all, I'll draw the scenario and then we'll develop out of that. So let's say we have some land here, we have an island here, we have another island, but that's far bigger island that extends to the right, so I'm not drawing the entirety of it. And then we have another part of land here. Now we have one vertex here, one vertex here, one vertex here, one vertex here. That's basically because I will translate this whole problem into graph theory language, where the basis of graph theory is vertices and edges connecting them. So that's the reason. But maybe before even looking at the vertices, let's first talk about, so maybe for a second we'll still do the vertices to make it all simpler. And let's just say, make sure that it's all understood. This is a part of land, this is another part of land, another island here, island, this is like a river, and there's this island in the river and another one. But this extends to the right more and we don't see the rest, but that's not important. Then we have another part of land. And now I'm going to draw the bridges as like lines between those land segments. So we have 2 bridges on this side of this middle island to the land here on the top, and the bottom land connected by another 2 bridges to this central island. Then this island is connected to this land by one bridge and to this land by another bridge. So that's the plan of the city. So we have in total 7 bridges, because there's one more, was forgotten, this one. So 1, 2, 3, 4, 5, 6, 7 bridges. So this one connects the 2 islands. Now, this is the part of the city that's analyzed. We have 7 bridges, and we're asking, if we start somewhere, can we walk? Is there any way that if we start somewhere, on this island or this island or this part of the land or this part of the land, if we start somewhere, can we walk across the city? So can we cross the bridges gradually by walking around in such a way that we cross all of them, but we don't have to cross any of them twice? And the answer is no, as I said. And the way I'll answer it is, first I will enter the realm of graph theory. So we will make an abstract representation of this real world scenario by drawing a graph. And the way we'll draw a graph here will be that I will imagine that those land segments are representing one vertex each. Those are the nodes of the graph. So this island is one node, this island is one node, this part of the land is one node, this one as well. Each is one node. And the bridges regarding those regarding the connections that they create the connections between these land segments that are represented by those in total 4 nodes are the edges between those nodes in that graph that we'll make an abstract representation of this out of. So let's draw the graph. So I'll draw the graph now. The exact shape of the graph, the way we have how many vertices we have and what edges connect which vertices, that's determined in advance. Or which vertices are connected to each other, number of edges, number of vertices, and the way how individual vertices are connected to each other is determined by the scenario already. The exact way we draw the graph can vary, but that's not the important part. So the graphs might look a little bit different, but the main part about the number of vertices and which vertices are connected to which other vertices out of the picture, that's already like settled before we would draw the graph in a particular way. But generally, I'll draw the graph in the way that's the most general look, or at least approaches that, in order to be very clear. So we have these 4 vertices and we have the bridges between them. Now I'll draw a graph of it. So I can draw this vertex, this vertex, this vertex, these 3 vertices, And actually, it's also good to give them names already. So I'll give these land segments names already now. So I can do A, B, C, D. This island is A, this part of the land is B, this part of the land slash island is C, this part of the land is D. And then these will be A, B, C, D, 4 vertices in the graph, 4 nodes. And then these bridges, we see this bridge connects A to B, this one as well, both will be an edge AB. This bridge connects B to C, so it's an edge BC in the graph. That's the way I'll construct the graph. And then from the graph, we'll draw the conclusions. We'll draw an explanation, or at least a slight explanation, or yeah, an explanation of why it is so, why our entire answer was no for the initial question. So the vertex B here, B, then I'll do vertex C here. I'll do the A a little bit to the left. That's the way this Konigsberg 7 bridges graph is usually drawn. And then D down here. Now, I will do the connection of these. All the bridges already here. When we represent it by graph, we will connect D to C because that's what really happens thanks to this bridge. This bridge connects this part of the line to this part of the line. That's the way one has to walk when one walks around the city. One is present at some part of the land, but then he eventually gets to the bridge to cross it. So, yeah. So now I'll draw edges where there are bridges connecting those individual parts of the land represented by the letters that the vertices are connected as. So we have D to C, so we have edge here, we have C to B, we have an edge here, we also have a bridge C to A, so an edge C to A, and then we have 2 edges from B to A, so I'll just draw them in different shape. This is the usual way one can draw it. A to D also twice, so one like this and one like this, and that's it. Now we have the Konigsberg 7 bridges graph. So now we have a proper graph, and using graph here we can look at different properties. So let's say that I want to list the degrees of all the vertices. So each vertex has a degree which is specified or defined as the number of edges connected to that vertex. So A has 1, 2, 3, 4, 5 edges connected, so its degree is 5, and so forth. For each letter it's going to be different for each vertex. Now, there is something called Eulerian trail, and that is the theorem that one uses to answer such a question. So once I have translated this to the graph, I can use the knowledge of what the Eulerian train is and what its requirements are in order to answer the question. So basically, Eulerian trail is basically a trail around that graph. We can say a walk where we move between vertices across the appropriate or across the available edges in that graph in such a way that we can visit the same vertices more times. So we can go to B more times or something, but we cannot, or to A potentially or something, but we cannot go across the same edge more times. So Eulerian train means we visit all the edges in the graph once and exactly once. Alright, so that's when we have a Eulerian trail across a graph. We visit all the edges once and only once. So there is a condition for the existence of a Eulerian trail on a graph. And now what is that condition? Well, first of all, we're talking about walking around a city or going around the graph and gradually moving one vertex to the next and going across all the edges, and also, by the way, precisely once across all of them. We need a connected graph, which means connected graph is there exists some walk from one point to another. A connected graph for any 2 vertices of that graph, there exists a walk between them. It means we can walk one by one across vertices to go from one to a distant other vertex on the same graph. If it wasn't connected, we have basically like we have some vertices that you cannot go to by a walk, and that's not what we are taking into account here. We see that in this city, of course, we can walk from any part of the land to any other part. We were actually concerned with, are we able to take a walk and walk across each of the bridges exactly once? and not more times in order to cross all of the bridges gradually, walking along the city. All right. So the Eulerian trail is defined like this, and if we are able to satisfy some conditions, then the Eulerian trail is possible in the graph. But let's see if it is possible in this one. So it's now useful to introduce those conditions. The two conditions, basically, first of all, it's supposed to be a connected graph, which it is, so that's satisfied. But another, and that's actually what would discourage us even in real life of even thinking about it. Like, but anyway, if we have a connected graph that's satisfied, we also need to make sure that either exactly zero, or exactly only two vertices have an odd degree. And all other are even, or in the case of zero, all are even. All the degrees of all different vertices of the graph. But we can see that in this graph, if we actually list the degrees, which I'll do now, it isn't satisfied. And for that reason, the answer to the whole question was no. So let's list the degrees of the four different vertices of this graph. So we have the degree of all of them. So we can do degree of A, degree of B first. So degree of A, as I said, count the amount of edges that it's connected with. That is the degree of the vertex. So that's 5. Degree of B is 3. Let's do degree of C and D. That is C has 3 and D has also 3. Now, as I said, Eulerian trail on a graph is possible if not only is the graph connected, but also exactly 0 or exactly 2 vertices only have an odd degree. But here we see 4 have an odd degree. So it would be possible if for example, all vertices in the graph had even degree, or exactly 2 vertices had all vertices had an even degree, or exactly 2 vertices of all of them had an odd degree. Then, in such 2 cases, Eulerian trail will be possible in that graph. But because this condition is not satisfied in this one, we see we have 3, 5, 3, 3, or odd. That's more than 2. Anyway, then it's not possible. So this way, one can answer it. And this is a generalization and very big help in analyzing more complex situations than this one. Let's say we have a more complex city that can be also represented by a graph like this, a connected graph. And now we're asking ourselves, can we have a walk across all the bridges between those parts of the land if the city is structured in a similar way? That's just more complexified. Can we actually walk across all the bridges in such a way that we don't have to repeat any of the bridges more times when we walk around the city? And the first step we can always take is count the amount of edges each vertex when we represent the city as such a graph. How many edges each vertex is connected to? So get the degree of each vertex. And if we know that the representing graph is connected and all vertices, for example, have an even degree, then we can say already yes, it's possible. But if 3 have an odd degree, then we can surely say no. So that's that. So that's a help. And now, one last thing. There's a change that has happened, and of course, throughout the time since this problem was first looked at, the bridges in the city have changed, but there's of course more bridges, but some have been removed and so on. Some are not there anymore, some are still there and so on. And let's say that either because in reality some bridge has disappeared, or we hypothetically could just remove some of the bridges from the scenario and re-evaluate the scenario, look at it again and see if actually it still holds that we cannot have a walk without repeating some of the bridges. Any bridge of them, any of them. Well, let's say that nowadays, if we ignore the other changes that have happened, there are no longer 2 bridges but just 1. So we could say we have this sort of situation, and then that would mean that we have a different graph representing the whole situation. I'll separate it now. I mean, this initially was used in order to create this graph representation, but no longer is it so. Now the graph will be slightly different. It will be exactly the same one, but we'll have one less edge between A and D and A and B, between both of those. So I can draw it like this. I can draw it like basically this. Alright, so now we have this. And now the question is, does it still apply that we cannot have such a walk? Well, actually, it no longer has that problem, because now that two bridges have been removed, the degree of the individual vertices has changed. And for that reason, I mean, C still has the same degree, but you see D had a degree of 3, now it has a degree of 2, A has degree of 3 instead of 5, but in general we see D and B have an even degree, and A and C have an odd degree. But now it's fulfilled, that exactly 2 have an odd degree, so it should be possible that there can be an Eulerier trail on this graph, and that we can actually get such a walk to work. And indeed it's possible. You can, for example, imagine A to C going like this and walking like this. We repeat some vertices, but we don't repeat edges. So we get to walk across, we have to walk to the same parts of the land perhaps, but we don't have to walk across the same bridge more times. But we get to cross all the bridges in that walk. So now, when there is not two bridges, but just one bridge between A and D and A and B, now there is a Eulerian trail, and this new graph representation proves it to us when we list the degrees of the individual vertices.